All right, so in this video we're going to discuss a topic called independence of path. In the previous one we looked at the fundamental theorem for line integrals, and in that case we saw that the line integral actually only depended upon the beginning point, the initial point, and the end point of our curve C. But as a reminder, in general, this is not true. If we take the integral over a curve C1 of f dot dr, that is not equal to the integral over a different curve C2 f dot dr if C1 and C2 are different paths with the same initial point and the same end point. So if I have a point here and a point here, and I travel from A to B along C1, and then if I take a different path along C2, these integrals should end up being different in general. And we saw an example earlier in the semester, a few days ago, that actually showed us this and gave an example where we went along two different paths and we got two different answers for a line integral. But again, in the previous section, or the previous video, we noticed that the fundamental theorem of line integrals actually said that this does happen, that these are equal, that we get a line integral over C1 of the gradient of f dot dr is equal to the line integral over C2 of the gradient of f dot dr, and those will be equal. But what were the conditions? So in general, it is not true that they're equal. However, under some certain conditions, it is true. And what those conditions were was that our vector field f was actually the gradient of some scalar function f. Okay? So here we have the gradient of a scalar function f that we are integrating. And when that happens, it again turns out that the integral only depends on the initial point and the end point of our curve C. And again, we saw an example of all of that in the previous video. So, when this occurs, we say that f is independent of path, f being our vector field f. That terminology, independent of path, comes from, it doesn't matter which path we take because our integral will be equal over those two paths. Again, with the condition that f, gradient of f, is the function we are integrating here, or the vector we are integrating. All right, so we're integrating over a vector field here, and if that vector field is the gradient of some scalar function f, then our vector field capital F is independent of path. Or in other words, line integrals of conservative vector fields are independent of path. Okay. Well, there's a couple of other definitions we need before I discuss the next thing. So here's those definitions. A curve is called closed if it has the same initial point and the same terminal point. Sorry, same initial point as terminal point. So I've drawn some pictures here. If we take a curved path here and it is closed, then it forms a loop. So we start at A, we move along this path, and we end back at A. So A and B, our initial point and our terminal point, are the same value, or same point. And if that's the case, then we call our curve closed. All right. Well, here is an example where it's not closed, right? We have a curve in space, but our initial point and our end point are not the same point. So this picture is a curved path that is not closed. Okay. Now, what we'd like to notice is that for a closed path on a conservative vector field, well, let's break this up. We have a closed path on a conservative vector field, and let's take some point A here and some other point B along this curved path. Well, the integral over C1 and C2 is really the integral of C1 of the gradient of f dot dr, because this is a conservative vector field, So it's really our vector field f, capital F, is really the gradient of some scalar function f. And so the integral over all of this is the integral over c1 of the gradient of f dot dr plus the integral over c2 of the gradient of f dot dr. But what is that? Well, since this is a conservative vector field, evaluating this just means we evaluate f, our scalar function f, at r evaluated at b minus f at r evaluated at a. And we add to that f evaluated at r of a minus f evaluated at r of b. And notice that then all of that cancels out and we get 0. So the integral over a closed path on a conservative vector field is always 0. All right. That brings us to a theorem that I want to end this video with, so let's discuss that theorem real quick. All right. So we have the integral over a curve C of a vector field f dot dr is independent of path in D if and only if the if and only if the integral over the curve C of f dot dr is 0 for every closed path in C. All right, and really what does all that mean? So if f, the vector field f, is a conservative vector field and C is a closed path, then this derivative is 0. That's by our previous discussion. Moreover, this theorem says the opposite is also true. So the only vector fields that are independent of path are conservative vector fields. All right. And we'll go ahead and end our video there.